Hi friends, welcome all of you to my channel on ST1. Today we are discussing a problem on shear reinforcement, the design of shear reinforcement from the previous question paper, October 2019. What's the question? A beam is given, a beam of breadth 250 and overall depth 430 mm is reinforced with AST is equal to 684 mm squared. That is given. AST 684 mm squared with an effective cover of 50 mm. Effective cover is given as 50 mm. Therefore, effective depth will be equal to overall depth D minus 50. That is 430 minus 50 mm is equal to 380 mm is the effective depth of the beam. Now, the grade of concrete is given as 20 Newton per mm squared and grade of steel 415 Newton per mm squared. And the factored shear force is given. The maximum shear force on the beam is given Vu, it's equal to 45 kilonewton. 45 kilonewton is the factored shear force. Right? The question is to design the shear reinforcement. First of all, check and if required, design the shear reinforcement for check for shear. Is it clear the question? So we have to design the shear reinforcement required for this beam. The data given breadth, overall depth and effective depth, area of steel, grade of concrete and grade of steel, and also the factored shear force, right? So how to solve this? First of all, number one, find out the nominal shear stress tau V. Tau V is the notation for nominal shear stress. What is nominal shear stress? Shear force divided by area. So that is equal to Vu divided by B into D, the area. The shear force Vu divided by area. Vu is given as 45 kilonewton. So into 10 raised to 3 Newton divided by B is given as 250 into D is equal to 380 M. Right? So first of all, first step, calculate the nominal shear stress. That's equal to 0.474 unit Newton per mm squared. We got the nominal shear stress. Now, what is the next step? Number two, find out the percentage tensile reinforcement. Number two, percentage steel. What is the formula? 100 AST divided by BD. We know that. We already done. Percentage steel reinforcement PT is equal to 100 AST by BD. Percentage steel PT is the notation. PT is equal to 100 AST by BD equal to 100 into AST is given as 684 divided by B is 250 into 380. So that is the percentage of steel reinforcement is equal to 0.72. 0.72 is the percentage of steel reinforcements. Now, according to for this steel reinforcement, percentage steel reinforcement from the table 20 of IS 456, table 20 IS 456. From the table 20 of IS 456, corresponding to this percentage of steel, we'll get the maximum or tau C max. That means number 3, find out the shear stress. The design shear stress or tau C max is equal to 2.8. From the code, we check it, 2.8 Newton per mm square. So tau V is equal to 0.474 Newton per mm squared, and tau c is equal to 2.8 Newton per mm squared. So that means the nominal shear stress is less than the maximum shear stress. Therefore, we have to design the nominal shear reinforcement only. The nominal shear reinforcement. So how can we design or provide nominal shear nominal shear reinforcements for this beam? That we have already done in the first question. For that, from the table IS 456, from the close 26516, I already told you 26516 from the close, the minimum reinforcement. The minimum shear reinforcement is given as ASV number 4, ASV divided by B into SV greater than or equal to 0.4 divided by 0.87 Fy. So that's the relation from the code to get the minimum shear reinforcement, where ASV is the area of shear reinforcement, B breadth, SV the spacing of shear reinforcement, 0.4 divided by 0.87 Fy is equal to 415 Newton per mm squared. So from this you will get, what is it, the value of ASV, and from that you can find out the SV value. That means ASV means we have to assume. So usually that we have already done two-legged stirrups, right? In two-legged stirrups, if we assume 6 mm dia, usually for stirrups, the diameter we can assume less diameter only, say 6 mm or 8 mm diameter bar. Suppose we assume that we are providing 6 mm diameter two-legged stirrups. 6 mm diameter two-legged stirrups, then what is the area? What is the area of two-legged stirrups? That is ASV. Then ASV will be equal to 2 into pi by 4 into 6 squared, where 6 is the diameter. 6 mm is the diameter of the reinforcement. That's equal to, say, 56 mm squared. So area of two-legged stirrups, stirrup reinforcement ASV is equal to, say, 56 mm squared. Therefore, now we can find out SV. We want to find out the spacing number 5. SV will be equal to what? ASV into 0.87 Fy, or 0.87 Fy into ASV divided by B into 0.4, where ASV is equal to 56, Fy is given as 450 Newton per mm squared, B is 250 mm into 0.4. So using this relation is obtained from the code only, right? We are assuming the shear reinforcement, the diameter as 6 mm. That you can assume either 6 or 8 mm. Accordingly, find out the area. So this one, when you calculate the spacing, maybe approximately 121.8 mm. The spacing of the bar, the spacing of the vertical stirrups. Then, you know, as per the clause from the code, to design the spacing of the bars, we have to check two more data. What are the data there? One is 0, this is first one, number 1, 0.75 D, where D is the effective depth, equal to 0.75 into the effective depth D is equal to 380 mm. That also you have to calculate. 0.75 D, where D is the effective depth, that is equal to 285 mm. 285 mm is the spacing as per this value, 0.75 D. And number 3, the maximum spacing is limited to 300 mm. As per the code, the maximum spacing of shear reinforcement is limited to 300 mm. So check these three values. Number 1, 121.8, second one 285, and third one 300 mm. So from these take the minimum value. So therefore provide 6 mm dia two-legged stirrups at 120 mm center to center. Right? 120 mm center to center. 121.8, we assume it as approximately 120 mm center to center. So that is the design of the shear reinforcement. Is it clear? So if a question asked like this, by giving the dimensions of the beam, area of tension reinforcement, then the shear force, the factored shear force, and also the properties of the materials, concrete and steel. First, you calculate the effective depth by deducting the effective cover. Then first find out the nominal shear stress tau V, VU by BD. Then percentage steel PT 100 AST by BD. Then next step, check whether this tau V and tau C, as per this percentage of steel from the table 20 is 456, it is 0.72. So according to that, tau C max is equal to 2.8 Newton per mm squared. So it is less, tau V is less than tau C max. Therefore, we have to design minimum shear reinforcement. As per the code, it is ASB by B into ASB should be greater than or equal to 0.4 by 8.87 Fy. From that, to get ASB, we have to assume the diameter of the bar. Here we are assuming 6 mm dia two-legged stirrups. So it is 2 into pi by 4 into 6 square is equal to 56. So here substitute ASB as 56 and Fy is equal to 415. Breadth of the beam 250 into 0.4. You will get the spacing of the bar SV. Spacing of the shear reinforcement SV 121.8. And check the other two conditions also, 0.75D, 285 mm, and maximum spacing 300 mm. Out of these three, take the minimum value, that's equal to 120 mm center to center. So provide 120 mm center to center, 6 mm dia two-legged stirrups. This is the method of designing a shear reinforcement when the factored shear force is given. Okay, it's clear to you? Right. So we'll wind up the class now. Again, we'll continue in the next class. Thank you.